Good morning. As you can see, I'm speaking on behalf of a large team of scientists and engineers from Environment Canada. This is a result. These are the results that we obtained from the 2013 airborne program in the oil sands. In fact, I'm only speaking to a relatively small portion of the data that we collected during this period, during this study. This small part of this data set that I'm talking about is on the VOC emissions. See, I'm trying to figure out how to forward. Okay. So the study was designed with the two goals in mind. One is to obtain the independent emission rates of the VOC compounds from an entire facility. And this is to use the airborne concentration and coupled with meteorological measurements and an algorithm that we developed at ECCC to determine, to turn the ambient air concentration measurements into emission rates. And so using that, we got able to calculate the emission rates, and with the results, then we can compare with what's reported. Now, this is a slide to show the current emission information that forms the foundation, the basis for reporting to the National Pollution Emission Release Inventory. And you can see the different categories in here, from SO2 all the way down to total particulate matter in here. And what I blocked out in green are the data that are considered to be more reliable based on SIMS measurements or the mass balance, material balance approach, or in some cases, the site-specific testing samples. Now, in the red, circled in the red, are the data based on more uncertain approaches in the case of reporting. And this you can see based on the engineering judgment, for example, or emission factor that are general, not necessarily specific to the facilities in question. So you can see in terms of the VOC, the reporting basis are based, a large part of it is based on methods that are less certain. And so for the aircraft study that we conducted, we actually made quite a large number of measurements, and these are fast measurements, mostly 1 second resolution. You can see that there's a long list of compounds that are listed in here. I will only be speaking to the VOC compounds that we measured. In this case, we have 20 species that are continuous measured from 2 to 5 seconds, and 154 VOC compounds measured in discretely collected stainless steel canisters. Now, these are the concentration measurements. In the meantime, we also have the wind measurements, meteorological measurements from the aircraft. And you can see that we actually need to make a combination of both type of measurements in order for us to derive the emission rates in here. And this is essentially the algorithm that we developed. And essentially, this is the way we turn our measurements into emission rates. And it is based on mass balance. So if you imagine there's an imaginary box in there, the mass should be balanced when whatever goes in should equal to whatever comes out. You can see that equation describes how these individual terms of the rates in there. Now, the terms on the right, we actually made measurements. We could actually evaluate each of the individual terms based on the measurements. Now, this method has been published in a paper that you could refer to in about a year ago now. And so, applying this method and compare with emissions that are most reliable in the facilities, in this case, SIMS measurements of SO2, then we can determine how good this methodology can achieve. Now, this is a plot on the of SO2 emissions from the CNIL Horizon facility, plotted as y-axis, and the measurement-based emission rates determined from the aircraft is on the x-axis. As you can see, that correlation is the R squared is 1. And so the slope is 0.95. So that shows you the accuracy of this methodology in this case. So we are quite comfortable with using this method going forward. Now, I mentioned that we have 20 continuous VOC measurements from the aircraft for which the TERRA, the methodology, is applicable. Now, I'm using one of these VOC species as an indicator for the others. And this is a plot of the ambient concentrations in terms of mixing ratio, determined around a virtual box as created by stacking up the aircraft tracks along each of the 4 facilities. And here, Suncor Millennium to the top left, CNIL to top right, Shell Muskeg and Jack Pine facility to lower left, and Synchro Motor to the lower right. Now you can see this is a concentration of toluene, one of these continuous measured species, and you can see the plumes from the facility downwind of this facility that distributed very clearly. That's one thing to notice. The second thing to notice is that the different sources for each of the facilities. You can see them, the plumes showed up at different locations on the what we call the virtual wall of the box. The third point you can see that is all plumes were captured by the aircraft flights. Now, applying the TERRA algorithm combined with combining the concentration measurements or mixing ratio measurements with the meteorological measurements, we can actually determine the emission rates in here. And you can see these are the individual rates that are shown for this compound. And what these rates are essentially the compound advected out of the box. Now, these are determined based on the meteorology. Now, you could also see on the lower right, I actually draw 2 extra arrows in here, and that indicates the amount of time that will travel from the sources from a facility to the plume interception by the aircraft. Now, during that period of time, we know some of the VOCs would have undergone oxidation. Okay, so for that, we need to do correction to trace back where the emission rates are and when it actually for the compound is emitted. So we are able to determine these emission rates for the individual compounds of the 20 compounds based on the continuous measurements. Now, remember we also collected a large number of canisters on the aircraft for each flight. So we could take a look at the correlation between the continuous measured and the discrete collected samples. And you can see that the blue line indicates the continuous trace, measurement trace, and the dots are the samples. And you can see the correlation is actually quite good. So that's a verification, in a sense, internal consistency check. But also, this kind of correlation gives us another means to determine the emission rates for the other non-continuous VOC measurements in this case. So plotted on here are the sampled, discretely sampled species versus the continuous sampling. Now we have done this, look through the 154 compounds and canisters from 680 samples and compare them with the continuous compounds which we use as a tracer. We can determine the regression ratio and then determine the emission ratio of the individual compounds to the continuous species. By doing so, we can then apply that emission ratios to determine, and also the emission rates of the continuous samples, to determine the rates of the 154 compounds. And we look through these one compound at a time, and in the end, we are able to determine the emission rates for the 4 surface mining facilities for about 73 to 90 species, individual compounds. Now, these are based on hourly emission rates over the aircraft sampling period, and that is typically from 1 to 2 hours. So in order for us to do some comparisons, we need to upscale the hourly emission rates to daily, to 24 hours. We do this upscaling by looking at, by correct for these variations in diurnal changes in the emissions from the plants and stacks, using SO2 as an indicator of the emission rates for the plants and stacks. We also use a temperature variation during diurnal temperature variation, and assuming, based on the physics, that the emissions from the tailings pond and the mine phases obeys the Raoult's law. Now, that's the upper limit of the variability that we expect. Now, in reality, we know that the diurnal variability in the emission rates should be smaller than the maximum that we estimate this way. So based on that, we're now able to determine the daily emission rates for the compounds from 73 to 94. Now, actually from 77 to 94 compounds. Now, we use a subset of these 77 to 94. In fact, 73 to 90 compounds. We add them at the 73 to 90 compounds, add them up. And that's roughly 50 tons to 70 tons per day. Okay. Now, the reason I choose those 73 to 90 is because some other compounds could have different sources, like biogenic sources. And so those few species are not included in this calculation. Now, we are able to do this for the 4 facilities. For the other 3 facilities, we have emission rates for only 10 species from the continuous samples. We did not have the enough canister samples to do the same calculation that we did for the other 4 compounds, and therefore we do not have what we call a total of the VOC compounds. Okay, so these are the results that we got. How do we compare these with the reported values? Okay, first of all, before I do the comparison, let's talk about the uncertainties. Now, we actually went through these each of the steps in terms of deriving the total emission rates on a daily basis for these compounds, and we determined that the uncertainties for the 4 facilities are roughly from 24 to 33%, and these uncertainties roughly can be broken down into these different 4 sources of uncertainties in here. First of all, the methodology itself is roughly about 6%. Uncertainties in the oxidation correction is roughly about 1%. The daily variability is roughly about 16% based on the different flights from different days. Uncertainties in the hourly to daily upscaling algorithms is roughly 23%. That's roughly by far the largest uncertainty that we have. So for an overall, on average of the 4 facilities of 28% uncertainties. Now, let's take a look at what's reported in this case. For 2013, the emission reports to NPRI as of last week is for the 4 facilities roughly on annual basis 20,000 tons per year for Syncrude, Suncor 9,500 tons, 4,300 tons for CNIL, and Shell facility for 2,600 tons. Now, these are yearly reports, and we actually look hard to see whether there are any daily reports, and of course there are none, because their daily reports are not required. So we have somehow, in order to make this comparison, we have to do scaling down from these annual reports. Now, initially, the simplest way is to divide by this number by 365 to get averaged daily emission rates. Now, of course, we all know that's only an approximation, and there's uncertainties associated with it. We know that seasonal variabilities in these emission rates, right? So we know these emission rates should be related to the production and also to the annual seasonal variability in tailings pond emissions, and also in terms of the mine phase emissions, because these are the largest sources for the VOC emissions. So by incorporating these seasonal variation in terms of production, in terms of tailings pond emissions, in terms of the mine phase emissions, we're able to determine the emission rates for that period of time when the aircraft was flying. Now, this data is based on the production data is based on the AER report. The seasonal variability is based on a CIMA report from 2010. Now, using this algorithm, we downscale the annual reports, and these are in red, also in the column in the table to the right. Now, our measurement-based emission rates have to be corrected for the mining fleet, because that's not part of the emissions to the NPRI. So we actually have to subtract that part out. And so that this difference, measurement emission rate minus the mining truck emission rate, is in the column in blue. And taking the ratio of the data in column blue and to the data in column red, you can see the ratio ranges from 0.7 to 4.5, depending on which facility we're looking at. Given the uncertainties in here that you can see, uncertainties in here, that's two facilities would approximately be in approximate agreement with the measurement results, and the other two facilities have some differences in here. Now, we take a look at a step further in terms of emission individual species, and you can see that this is a relative rate contribution to the total VOC emissions. Red in measurement, blue and green in reports, and you can see there are quite a bit of differences in here in terms of the profiles. These are only a part of our total measured of all the species that we measured. And as you can see, there are differences. These are relative differences, but if you take a look at the absolute differences, you can see that the differences by species are substantially different in this case. The reported values are in the y-axis, the measured species are measured on the x-axis, and this is a logarithmic scale in this case. You can see that some of these differences are quite substantial. So if you take a look at the median values for each species, for each facility, we can see the in here in this report, in this slide, in fact. So to summarize, this is a new method that we apply to the oil sands facilities. We are able to relate the ambient measurements to the emission rates. We are able to determine the emission rates of total VOCs for 4 facilities. Compared to the report emissions, the difference is a factor of 0.7 to 4.5. We know for 90% of the VOC, single VOC emission reports, the differences are quite large, ranging from a median of 4.5 per facility to 375. Now, we also look at these species that were not reported, but we were able to determine. It looks like, depending on which facility you're looking at, then between 9 to 56 VOC species that would have met the reporting requirement, but not in the actual reports. And we think this could be due to the judgment, using the currently accepted method, they may have been deemed not meeting the reporting requirement and therefore not reported. And so that slide is that we actually are planning on our next phase of study, hoping that we'll get support from the JASM, but I will not go through these details.